zones where there was a single penetrative foliation. Thank you.
Any other question? No.
I couldn't exactly distinguish which part is from the published one and which is your own work. That's why I'm asking.
Okay.
That in the Tathian part, that is above the so-called quote-unquote channel flow, what are the folds consistently not diverging?
Sir, actually in the Tathian Himalaya, we have both top to the south-southwest directed thrusting on north-northeast dipping foliation, as well as top to the north-northeast asymmetry on north-northeast dipping foliation. That is, we have both reverse as well as normal shear senses. Studies suggest that the reverse shearing actually precedes the normal shearing event.
No, my point is that in the channel flow situation, we also did some experiments way back in 1990s.
Okay.
So if the channel really some channel flow is going on at a deeper crustal or mid crustal level, then many people have suggested from field studies also that in the top part of the orogenic wedge there should have been a backfolding. That means the vergence of the fold should be reversed to the direction of orogenic movement.
Exactly,
you
sir.
See that?
Sir,
here?
that's why we get the normal sense there. No? So, from this, as we move from the central part of the channel towards the South Tibetan detachment, that is the upper part of the I would rather use the term GHS because there are still controversies regarding whether it's actually a channel flow or there are some other processes also operating simultaneously along with channel flow. So, I will use the term GHS. So, as we move from the center of the GHS towards the upper surface of the GHS, actually we get normal asymmetry.
No, that I understand because if there is a channel flow, the hanging wall will be
exactly as the center will move.
But above that, I mean outside the so-called channel,
yes,
in the overlying Tathian sediments, do you see a reorientation of the folds?
Yes, sir. There are reoriented folds actually.
Okay, thank you, Shubham.
So we now come to the final talk of this session. So it's my pleasure to invite Professor Shobhit Chakraborty from University of Bochum in Germany, and he is going to talk about thermally pulsed processes.
For slide change and this is for pointer.
Okay. Thank you. Can you hear me? Yeah. Okay. So yeah, it's a particular pleasure to be here and be able to give a talk because I've given talks in many places in the world, but the last time I remember standing here was related to more like Birinchi Baba and Bhushundir Math, and I think Dr. Shah would be pleasantly surprised and even shocked that I'm talking about geology out here. So my talk is about the thermally pulsed processes. So let me start by saying what I mean by that and why we should deal with that. So consider any thermal process in a crust or mantle or wherever. It could be a magma, could be a metamorphic process or whatever. But as soon as you put a thermal pulse into a surrounding, you trigger a lot of different processes. For example, you trigger conduction of heat or convection of heat. At the same time, if you heat things up, you trigger chemical reactions. And all of those involve heat transport, volume change, and they change the state of stress and strain. And those in turn, depending on the nature of things, could produce fractures. And if that happens, the fractures in turn could guide fluid flow and things like that. And that back influences conduction, convection, heat flow, and so forth. So as you see, all of those processes, the thermal, mechanical, and chemical, need to be coupled. And what you see also in small letters on those is that all of these processes occur on different rate constants, K1, K2, K3, and so forth. And they occur on different time scales, T1, T2, T3. Now, as soon as you have that, you cannot avoid having a hierarchy of time scales. So you can start a process, you can go to the peak or the maximum of it and go down. So that's given by the purple line there on a time scale T1. But because all of these different processes are interacting on different time scales, you have a pattern shown by the green or the yellow curve. You have other time scales, T2 and T3. And usually using isotope decay, we measure dates and times on the time scale of T1. But if you try to get to the smaller time scales, you have to rely on kinetic processes, things like diffusion chronometry. And what I'll do in this talk is give you two examples of where that comes in. Now, that becomes also particularly relevant in terms of getting research funding and research grants, because one of the questions you always have when you're dealing with high temperature processes is, how does it relate to anything that humans can relate to? And these are processes that are on human timescales. So I'll start with the first example. This is a night picture of the area around Naples. And all those black patches are volcanoes which are potentially active even today. The big black patch on the right is Vesuvius. On the left, you have a red area surrounded that continues on outside of the picture is the Campi Flegrei. And you see an image of what happens when Vesuvius erupts today. This is from 1944. You see Naples in the foreground. So you'd like to know about it, know about the time scale, know about, get some warning. So let's start with the most iconic. If you talk about high temperature processes, this is by far the most iconic process that you have, the eruption of Vesuvius that buried Pompeii. And what you see here is the city of Pompeii, a major tourist attraction as it has been excavated today. And this has literally been scraped out millimeter by millimeter to produce what you see there today. And on the background, you see the twin peaks of Somma Vesuvius. Now, that of course was covered in layers of tephra, which you can go to the field and study today. And what you see immediately is that, although it was one eruption, it is not one particular rock type that came out. In fact, on the bottom left and other layers, you see different colors of tephra, gray and white and so forth. And if you plot them up petrologically, you see that actually that spans the entire, on the task diagram on your left, you see it spans the entire differentiation series almost, that one single eruption, okay? And on the diagram, you see various points. So the black points are compositions you get from melt inclusions. The green points are what you get by phase equilibrium experiments from analyzing the erupted tephra, the phonolite and tephrophonolite and so forth. But nothing covers the whole span. And now with thermodynamic modeling using things like the MEL software, you can actually get a continuous sequence, open symbols that reproduce a whole sequence and also reproduces various chemical trends. You see calcium, aluminum, and things against function of temperature, function of magnesium, and so forth. So you can take those and take the data and work out the temperatures, and what you see there is that there's a different color coding there. The three main types of rocks that you see in that eruption, there are other kinds, minor kinds, are phonolite, tephrophonolite, and brachybasalt. And phonolite is a white pumice, tephrophonolite is a gray pumice, and then you have brachybasalt. And what you do is, as you see in the next slide right away, that you don't actually get things close to equilibrium very easily. So you need to do work to figure out what's in equilibrium, how to get the temperature. So what you see here in the color codes are the main different rock types. So for example, in deep brown are the brachybasalts that are about 1100 to 1150 degrees centigrade. Then in the orange is a main phase, which is a tephrophonolite, which is around 1000 degrees. And then the yellow and the green are the white pumice, that's more like 900 degrees centigrade. So if you look at these rocks, so these are now clinopyroxene crystals picked from one single layer of tephra. Okay, and what you see immediately is just backscattered electron images. So the contrasts depend on the iron content of the pyroxene. And what you see immediately is there are all different kinds. I mean, there are no two single kind that's very similar. So there's a lot of different kinds. So that used to be, so nothing that's in equilibrium with the melt, and you talk about a phenocrystal. So nowadays we talk about the crystal cargo of a melt that's brought up by the eruption. But with that information, you have a lot of information that you can do a number of different things. So I'd like to spend some time and take you through that. So first thing you can do is you can go to any one of those and take a composition here. and use different thermodynamic tools to associate that composition with a particular set of thermodynamic variables: pressure, temperature, oxygen fugacity, and so forth. We call that the magmatic environment. Second, you have a chemical stratigraphy here. You know this one came, and then the light one, and then dark one, and then the light one again. So you can work out what came after what. You know the time sequence. And the third thing is, because all of these things are happening at those temperatures between 900 and 1100 degrees, if you put two compositions next to each other, they're going to try to diffuse. So you can model the diffusion and try to figure out how long they were sitting in any one of those temperature reservoirs. So first of all, you take a lot of these crystals and you work out these magmatic environments, and you get this sort of abstract diagram, which is magmatic environments. The different colors are the same colors that we were using before. So different magmatic environments, and it tells you how they're connected, where you had much more crystal transport which were not so connected with each other, and so forth. And based on that, again, you can go back and create the plumbing system. And this is now, after all these years, I mean, Vesuvius is one of the most studied volcanic systems on planet, and it is only now that we're getting to this kind of a plumbing system. So you have a picture where you have the moho at the bottom in the green here, and then the limestone layer on the top on the crust, and you have the mafic magma coming from the melt, the main tephriphonolite reservoir here. The mafic magma triggers things to bring things up to a shallower 5-kilometer depth magma chamber below Vesuvius, and then finally you trigger the eruption. So you get a much more detailed picture of what was going on and how all these different compositions are related to each other. But we'd like to do more. We can get timescales from that, which we have done. So now you can go and work out how long before the eruption things were moving into those magma chambers and causing different effects like earthquakes. And these are a plot of the timescales that you get from going from 7980. The eruption is here. So before the eruption, how long ago you are seeing different signals of magma movement. And what you see here is that about 10 years before the eruption, you had a lot of earthquake activity. And this is a great place to do this kind of geology, because usually when you do that, you come up with 10 years and people say, what is the uncertainty? How well do you know the 10 years? Now in Vesuvius, we actually have historical records, lots of historical records. So these are two quotes that I forgot to mention in the early slides, that this work is done with a lot of people in the INGV, in the Italian Volcanic Observatory. So they are people who know Latin very well. There are actually people who are archaeoseismologists. They study these kind of things. And there are very famous historical records from people like Seneca, Pliny the Younger, that talk about a lot of earthquakes 10 years before the eruption, that the Pompeii was basically a construction site before the eruption happened. And in fact, for those of you who know the Last Days of Pompeii, a famous novel and film, that actually has earthquakes in some prominent scenes in that story. So that's one thing you can do. You can work out the timescales, and that's very relevant going back to Naples today, because if the plumbing system has not changed a whole lot, and you can do things nowadays to check whether it has, then you know what kind of heavy earthquake activity and things you might expect before an impending eruption. So that can help the monitoring activities that are in great detail there. Okay, so with that, I'll switch to the second part of it, which is a ore deposit. This is now a ore deposit in northwest China up here. So this is China, this is northwest China here. This is a Kalatongke ore deposit, and the bottom here is a cross section with a scale. Eiffel Tower as a scale here, so that's the size of the body. And this work is done with Yajing Mao from the Chinese Academy of Sciences, and I obviously haven't gone to the field. I've just worked on the minerals and thin sections. Now, the previous work was done with clinopyroxenes. This is now olivines. So what you can do is you can look at olivines, and the difference here that I want to bring up is that in the clinopyroxene, we're looking at diffusion of one element. Here in the olivine, we can look at a multiple set of elements. We can do that on clinopyroxene as well, but in olivine, I'm showing you that. So this is now things like nickel, magnesium, manganese, a number of different elements in element concentration maps. And if you take all of those and plot up the profiles, this is now a very busy slide, but I'll take you through three different aspects of it. So on the top panel there, right about here, you see what are measured element profiles of so-called fast diffusing elements, things like nickel, cobalt, magnesium, manganese, and so on. Then on the bottom panel here, you have data points from the same olivines of things that diffuse slowly, like phosphorus, chromium, aluminum, and so forth. And if you look at the top profile here, you see red lines. Those are the results of modeling these things with diffusion. And you can use the same diffusion model, first of all, to fit all of those things. Now, in something complex like that, you always have the question, do you know this is profiles formed by diffusion, or is it forming by crystal growth or fractionation or something like that? That's always a question. But what you can do now is on the third panel here, you can look at the fractionation of iron and magnesium isotopes along those profiles. And that happens only if you have diffusion, and that is also modeled with the same models that are modeling the elements, and you can see you can fit those quite well. So you get a very well-constrained, tight diffusion model on that. Now the slow diffusing elements, they help you to figure out what the initial profiles look like, and you see sharp discontinuities here in many places, and that would be interpreted as multiple stages of growth in most situations. So what I want to show you here is that you actually take that and you can do the thermodynamic modeling of this gabbro-norite, and you cool it and fractionate it along at 1 kilobar nickel-nickel oxide buffer and 3 wet% water. Along the cooling path, you produce many different, obviously many different mineral assemblages: olivine spinel, olivine plagioclase fluid, olivine plagioclase clinopyroxene fluid, orthopyroxene plagioclase fluid, and so on. And it turns out that all of those element jumps and things are the consequences of changing assemblage during the cooling of one simple thing. So that gives you a very tight constraint that this whole body was one single magmatic pulse that was cooling and producing these assemblages. And you can also say that along the middle of the intrusion, it cooled slowly. This is temperature against time. And on the rim of the crystal, it cooled more rapidly, as you would expect. And what that tells you is that that magmatic body and the ore deposit is a result of one magmatic pulse, about 100 meter thick, and cooled over 100 years or so, 60 to 150 years, something like that. Okay. Now, to check that, you can do a thermal model. So now things are, interrelated. So you can do a thermal model, put in a dike in the crust at the condition, and see how long it takes to cool. And again, if you take the right size of the thing, you get a pretty good fit for a 50 to 80 meters dike or so. So that would be a situation where you have a base geothermal gradient, and then you put in dike-like intrusions where you can cool the things and produce these ore deposits. Now there are similar ore deposits about the right size, but bigger ore deposits, more concentrated, and the idea would be that those would then be multiple pulses within the same dike feed, and that gives you an idea of how the mineralization may happen along the fractures and things that are happening in that cooling pluton, and where you can use then fluid flow and structural geology to work that out if you know the geometry of the process that's happening. So with that, to work the whole thing out, you need to work on petrology, geochemistry, thermal models, structural geology, and fluid dynamics all together to work out things like location of ore deposits in that case. But more generally, you need to think about thermal, mechanical, and chemical aspects together. And that would be very much in the spirit of what Dr. Shah used to do. He was a big fan of interdisciplinarity, so that's something he would be very happy with that we do. Thank you.
Thank you, Shumita, for the extremely interesting talks. I'm sure there will be questions, queries from the audience. So I have one question.
Yeah, go ahead.
So for the first example that you talked about, the clinopyroxenes.
Yeah.
So how did you reconstruct the magmatic environment of each individual growth zones?
So you because you know because you know the cooling history of the whole thing, you know what composition of cyanopyroxene will be forming when, and based on that, once you have a particular composition, you know where it is forming, and as you see, it's not one particular crystal is not necessarily forming along a straight cooling path. It moves between those different environments. And so the idea would be that
So you model it, right, essentially?
so this you extract. So you see, for example, for Me2, you have magnesium number within 81 to 64, aluminum weight percent 11.2 to 8.6. So those are conditions at which you make these kind of rocks at that condition. And then because you know that, let's say Me2 is this one, so if the next one is Me1, then you know that the thing is moving from Me2 to Me3 or whatever. So that's where all these arrows come from. So each arrow comes from one crystal, and the whole totality of the crystals gives you the picture.
Do you also estimate the PT conditions of each of these zones?
So the what?
Pressure temperature conditions.
Yeah, we express the pressure temperature of each one of those zones.
Thank you.
And you use that to do the diffusion model. Yeah?
So any other question?
Will there be any change in the this environments that you have deducted from the reams, different reams? Will there be any change from the central part to the outer part of the volcanic conduit? I mean, this kind of changes.
Yeah, there may be. So as you see, this is a very broad picture. So the conduit would be one line on this, any one particular conduit. So within the conduit sometimes, I mean, not here, but in other cases, we have thin rims that form, very thin rims that form on the very last stage. And you can see that. So for example, in Mount Etna, you have eruption along the central conduit and things that are lateral eruptions along lateral vents.
No, in the central conduit itself, because I'm not a volcanologist, just I'm trying to visualize that the central part will be hotter than the part which is in contact with the wall rock of the conduit?
Not during such an eruption. During such an eruption, in a conduit itself, the melt moves up so fast that it barely changes changes pressure, of course, but the minerals don't get time to react typically.
So we have one more question at the back.
Thank you, sir, for your talk. Sir, let's speak about this image. The image, please. The slide, please.
Sorry, I didn't.
Sir, in case of this image, we are. Am I audible, sir?
Yeah.
Yes. In case of this image, we are having a central conduit. So, if this is a recent scenario, right? If we backtrack it in Precambrian or let's say Precambrian, so the whole area will be eroded out, and in a volcanic plumbing system, there are certain places where sulfide saturation is reached, and we get sulfide droplets which come out as often come out with second boiling with magmatic hydrothermal fluid. They come out. They penetrate the structurally weak zones and emplace in economic bodies, ore bodies. Now, is it possible, and this volcanic subsurface magma chambers can be hundreds of kilometers large. But when they are taking out or scavenging the metal towards the surface, can it be a single point or 2-3 kilometers large ore deposit and no absolute occurrence elsewhere?
So that's a lot of questions. Let me try to split it up into 3 parts.
Yes.
So the first is if you can use this tool in the Precambrian. Yes, you can. I mean, that's one of the biggest powers of this tool that people have used this even in meteorites. So all you need is a few crystals and then you reconstruct things. So that's, and the age resolution doesn't go down with the age of the system. So you can resolve a week or a month back in the time of a meteorite of 4.5 billion years ago or whatever. In isotope systems, your resolution becomes worse as you go back in time. So that's actually one of the biggest advantages of this one. So the second thing is that whether you see the difference between sulfide or not, now this is at the very beginning, this is the first work we have done, but what you see here are some olivine maps of some crystals, and there you do see difference between olivines that are in the silicate part of the rock versus the olivines that are in contact with sulfides. So for example, in an element like nickel precipitates, prefers to go in the sulfide, but in a silicate, the nickel is more compatible in the olivine. So you see opposite diffusion, zoning trends and so forth. So you can try to, develop that and do that. So that's not been done, but could be done. And the third thing is about the size of the deposit. Now that's where, you need to bring in other aspects. You need to bring in physical modeling or something. What you can do with this tool is you can map out the cooling rate, like you saw in this example here. You can distinguish between the center of the intrusion and the margin of the intrusion. So if one does more of that modeling, you could try to work out how large a body was or whether it was continuous or not. But that would require, of course, a lot of outcrops, and that's the other problem with Precambrian things. You don't have large continuous outcrops. If you had that, one could try to do that.
So why I was asking this question, we all know about the Malanjkhand copper deposit, right? So GSI is working on it, and we in our sinks we try to analyze the sulfur and oxygen isotope of Malanjkhand copper deposit. Now the sulfur and oxygen isotope signature is purely magmatic. There is no heat of subduction which has been previously proposed. If there was subduction, or if there is a larger magma plumbing system below, then it should have several offshoots associated with the main Malanjkhand copper deposit, because hydrothermal fluid, it will penetrate any structurally weak zone. But it didn't. I mean, there is no significant satellite deposits around Malanjkhand. So what happened in that, because we have similar structural setup, similar kind of joint sets, similar kind of fracture zones around them, but we don't have Rasak in Malanjkhand. So when you were saying about the Vesuvius, it literally stands as a point on map. Right, but the magma chamber below it is much larger. So when I was asking on that perspective whether it was similarly happening in the Precambrian or not. Although Vesuvius, I don't know whether it poses any economically viable deposit. It probably doesn't. But whether similar process also operated in the Precambrian or not, and all the hydrothermal fluids couldn't reach into the surface, just as a point. So
I mean, that would largely be a problem of modeling fluid flow and things like that, so more physical problems. And in the Precambrian, the only thing I can imagine quickly is that you probably had different thermal gradients or not, depending on how old in the Precambrian. And that might have affected the nature of fluid flow that you have today versus then, but that's really not something I'm an expert on, but it'd be an interesting thing to pursue. And what we could do with this is to check out if the time scales on which these things cooled or were hot were different or the same along the various separate occurrences that you are talking about. So that's something one could try to do and see if that tells something.
Yes, thank you, sir.
Okay, so thank you, Shobita, for the wonderful talk. And with this, we come to the end of this session.
Thank you.
Yeah. So, my thanks to all the speakers for the excellent presentations. And we enjoyed sitting here. We also enjoyed the presentations and the questions and answers. Thank you very much.
Thanks to the session chairs and all the speakers for this wonderful session. Now, I would like to request Professor Gautam Ghosh to deliver the mementos to the keynote speaker and the session chairs. I would like Professor Anupam Chattopadhyay to please come on the dais. I would like to request Professor Somnath Dasgupta. I would like to request Professor Devashish Upadhyay. I would like to request Professor Anupam Chattopadhyay. Now we will gather outside the auditorium for tea session, and that will be followed by the poster session. We will meet again by 7 o'clock in this auditorium for certificate distribution for both the oral and poster presentation of today's sessions. Then there is a small cultural program that will be organized by our students, Orkunil and Doibangshu, and that will be followed by our students' dinner. Thank you.
check, hello, check 1 2, hello, check.
বসবি তো তো আমি ঢুকবো তারপর তো তোর ফোনটা এখানেই ছিল লক্ষণ করি না তোর ফোনটা ভারী ভারী আর মিশা একটা ভালো যে আবার এই চার্জের চাপাটা ফাটা হলে চার্জারের পিনটা তখন অরিজিনাল গান এটা চেঞ্জ করে কি কাজ আছে ডিসপ্লে কেনা থেকে অরিজিনাল গাড়ি লাগিয়ে দিতে হবে হাজার 2,000 টাকা তিনটে মডেল আছে তিনটের মধ্যে যত ভালো মডেল ওই লেদার সেটা পিছনেও তো লেদার মডেল শুধু এই কালার তিনটে মডেল তিন রকম জিওটা ওটিপি সাবস্ক্রিপশন দিয়েছে ফাইবার এয়ার ফাইবার না এটা আছে এইগুলো হটস্টার মশার তো দেখছি পরিস্থিতি শেষ হয়ে যাবে এক্সপায়ারমেন্ট 22 এপ্রিল না বেড়ে গেল কি জানি 22 মার্চ ছিল আমি কালকেও দেখেছি সিরিয়াসলি 22 মার্চ ছিল এইগুলো অল্ট বালাজি মানুষ
You just
অল্ট বালাজি
Hey, please come.
তিন সাইকেল ইন্ডে
1 minute. মোবনে দি
ওইটা তো সাবস্ক্রিপশন নেই দেখাচ্ছে কেন আমি লগ ইন করতে পারছি না অ্যাভেলেবল করতে পারবো আমি কেন তোকে বলছি মার্চ মাসে 22 তারিখ আমি তো ভালো করে দেখেছি আমি আইপিএল 22 তারিখে শুরু হবে আর বলবো জিও হটস্টার ছাড়া 22 তারিখে এসে জিএর চ্যানেলেও তো খেলা দেখা যায় তাই না এটা 599 টাকা 600 কত টাকা আছে এইটা দিয়ে কোথাটা নেটফ্লিক্স আমি আর ডাটা রিচার্জ করবো আমার এখন ডেলি আমি পাই 1.5 GB করে কিন্তু আমি আর করবো না ইনভেস্ট করি ঠিক আছে বাড়িতে আমার বাইরে আর কত ফোন তো বাড়িতেই ফোন দিয়ে ডাউনলোড করি সবাইকে দিয়ে দিই, ঠিক আছে, কিন্তু তোমার কপাল ভালো থাকলে তুমি কানেক্ট করতে পারবে, পোলট্রি যদি খুলে দেখতে শুরু করে আর কানেক্ট করে। কপি করতে পারছি না।
तो आपका है जैसे मतलब वो जो है कौन है कहने की
আমার তোমার নেট
हाँ actually finding the person we are actually finding the person
খুলে
What is your name? Rita.
আমি শুধু যেতাম, গেলাম সিগারেট মিগারেট সব বাড়ি পড়ে এইদিকে বিটি রোডের সিটি মোড় বাড়ি কলেজে কী সব কৃষক পড়া পেপার টেপার দেখি আমাকে বললো পেপার আছে বাড়ি যাবো না বলছে কাল যে ঠিক আছে কথাবার্তা বলি, তারপরে খাওয়া দাওয়া করে ঠিক আছে, পরে দিন সকালবেলা ফোনে এসেছি আমার সঙ্গে কথা বলছি, আমি তাকে শিয়ালদা আমি দেখা করতে ট্রেনে করে আসতো শিয়ালদা করতে আমি তো শিয়ালদা আমার দেখুন বঙ্গবন্ধু কলেজের ব্রিজটা ব্রিজ থেকে গিয়েছি এখানটায় নামতো ট্রেন থেকে নেমে বাইরে বেরোতো আমি যেতাম সিগারেট খাওয়াতো সিগারেট খাতাম সিগারেট আমিও খাইতাম আমার নেব আমি খাতাম ও খাতাম সিগারেট দিকে ওই মেয়েটাই খেয়ে তো সিগারেট খেতে খেতে মানে পরের দিন সিগারেট খেতে খেতে কথা বলতাম কথা কথা বলছে আজকে আমি কাল থাকবো কালকে তুমি চলে আসবো এবার আমি বললাম আর কি চলো যে ঠিক আছে শিয়ালদা থেকে কত দূরে কথাবার্তা আমি চলে গেছি আমার অফিস চলে এসেছি কলেজে গিয়ে আমাকে ফোন কখন এবার তুই এতক্ষণ পর্যন্ত আমি জানি তারপরে কলেজ থেকে বাড়ি চলে গেছে লোকেশন পাঠিয়ে আমি চলে যাবো বলছি ঠিক আছে তাহলে কি খাবে না আমি বলছি রাখতে তো আমার ঘরে রাখবে বলছি না আমরা এখানে থাকবো এইবার আমার একটু ডাউট কতক্ষণ প্রোগ্রাম করে সবাই যদি কালকে রাতগুলো বারবার আমরা খেলে পরে খুব ইচ্ছে একসাথে থাকবো আটটা সাড়ে আটটা হয়ে গেলে আমি তখনও যাইনি আমি আর ফোন বন্ধ পরের দিনকে আমি একদম ফোন করেছি এখন তো লাগিয়ে দিচ্ছি লাগিয়ে ভালো হ্যাঁ 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 দাদা আনন্দ ছিলাম দেখছি একটা রাত্রি দুটো রাত্রি একটা রাত্রি ও ছবি বের করে ঘোটানো হয়ে গেছে ইতিহাস সিনটা কেটে দেবো এইবার আমি বলেছি শরীর খারাপ হয়ে গেল ঠিক আছে পরের সপ্তাহে তো আমি আবার একটা এই ফেলে করেছি আর কদিন বাইরে কথা কথা ভুলে গেছি আবার পরের সপ্তাহে একদিন এরকম করে দুবার তিনবার আমি কাটিয়েছি ঘরে বন্ধ কথাই বলি অনেকদিন কথা বলিনি তারপরে তো তারপরে মাস 4-5 3-4 পরে এখন মোটামুটি কথা বললে যে কথা বলবে না এরকম এখন ঠিক আছে
No, the thing is that
প্রথমবার
in Mashi area, we do not have that kind of quality. I don't know that.
না অন্য ছেলে হলে অন্য ছেলে হলে এক্ষুনি যাবো বুঝলি কি তখন ব্যাপার মানে সেটা নয় মানে এইটা ভালো কিন্তু কথাটা কিন্তু উল্টো পাল্টা কিছু হয়ে যাবে তখন জড়িয়ে যাবো না ব্যাপারটা সেইটা তো ঠিক না। সেই কারণের জন্য তখন সাহসটা আরেকটা মেয়ে ছিল বিয়ে একটা বরুণিমা বলে একটা মেয়ের সঙ্গে বহুত দিন প্রায় 12-13 বছর তখন আমি ক্লাস 10-11 ট্রেনে পড়ি এরকম ভালো মানে আমার সব এরকম এরকমই প্রেম হচ্ছে জানিস আগের আজকালটা না আগের দিন যেটা বললাম এদের সঙ্গে প্রেম না। আমি আমার বউকে বাদ দিয়ে আমার লাইফে সলিড যদি বলতে হয় যদি ঠিকঠাক হতো তাহলে আমার বউয়ের আগে আমার লাইফে দুজন ছিল মানে যাদের সঙ্গে আমি প্রেম হয় চান্স খুব ছিল হয়ে যেতেই পারে কিন্তু হয় এই আমার বউ 3 নম্বর মানে ভালো আমি পাচ্ছি দেখতে গেলে আমার বউকেই করি বিয়ের আগে যে দুজন ছিল তাদের সঙ্গে ভালোবাসা হয়ে যেতে পারে কিন্তু মেয়েদের সঙ্গে খুব ভালো ছিল হয় একটা হচ্ছে যে আমার সব ক্লোজ বান্ধবী আছে তুই না বলে যাকে আমার বউ ছেলে পুলিশ সেখানে ঠিক আছে ওর সঙ্গে আমার খুব রিলেশন হতে মানে ভালো 2 তারিখ থেকেই ওদের কাছে ভালো কিন্তু আমি নিজে থেকে করেছি এখন ওরা খুব ভয় ওর বাবা পুলিশ দাদা হাই স্কুলে দিয়ে ঠিক আছে মাও কি একটা কাজ করে সব গভর্নমেন্ট সাইড আমার তো ওটাই নেই ওদের লেভেল এখানে হলো আমাদের বললাম আমার লিঙ্কার আমাকে জেলে পড়ে দেবে আর না হলে আর সেই আমার একটা ভালো পজিশন সেই আমাদের তারপর থেকে আমি সেই সব দিক থেকে জানি ক্লোজ বান্ধবী এখন ফোন করলেই হয় আর একটা মেয়ে ছিল